Nice. So let us now continue our discussion regarding our sample problem last time. So we have the integral of 3y minus 1 dy all over y squared plus 2y plus 2. And we say that this term here is also equal to y plus 1 squared plus 1, right? So instead of this, we simplify our equation as 3y minus 1 dy all over this one. So y plus 1 squared then plus 1. And then from here, we use the change of variable, wherein we let let me change the variable to z. Let z is equal to y plus 1 squared plus 1, and then we take the derivative of this, that is equal to 2, then y plus 1, then the derivative of y, which is the y, and because the derivative of 1 is just 0, right? Then from here we divide both sides by 2. That's why we have the remaining y plus 1 dy there. But as you can see, we don't have any y plus 1 dy at the numerator, but instead we have 3y minus 1. So our technique last time is to separate these two, 3y dy, and then all over this whole term, and then minus 1 dy all over this whole term. But this time, let us try another solution by transforming our numerator to have this value, to have 1 plus y plus 1 dy. Okay, so all we need to do is to transform this 3y minus 1 equal to something that has y plus 1 in order for us to use this later, right? So how can we do that? So by simply analyzing this 3y minus 1, so we have y plus 1. So we have at the left side of our equation, we have 3y. So maybe we can multiply this by 3. If we have that, then if we multiply this whole term by 3, we have 3y times plus 1 times 3 is just 3. So we have 3y plus 3. Then how can we make these two equal? So we have 3y minus 1. So they are not equal because we have 3y here, we have 3y here, but we have plus 3 here and we have minus 1 here. So all we need to do is to add some constant here. Okay, so as you can see, we need to add negative 4. Okay, so if we add negative 4 here, then 3y minus 1 is just equal to 3y plus 3 minus 4 is just 3y minus 1. Okay, so they are now equal or the same. So we can use this as a replacement to our 3y minus 1 because they are we proved that they are equal. Okay, so if we do that, then our equation or our integrand will become, instead of writing 3y minus 1, we can write this 3y plus 1 minus 4, and then of course our dy all over our denominator, which is y plus 1 squared plus 1. Then from here we can now distribute, and we have 3, and let me 3 y plus 1 dy all over y plus 1 squared plus 1. And then we also have the minus 4 integral dy all over y plus 1 squared plus 1. Okay, then from here you can now from here we can now use our formula, because we have the formula for this two, right? So this 3 integral of y plus 1 dy there all over y plus 1 squared plus 1 so we have this side here. It's just we say we use to the change of variable when we let z is equal to the this whole denominator y plus 1 squared plus 1, and then we have the dz is equal to 2y plus 1 dy, and then we divide both sides by 2. Yan. And as you can see, we have the term y dy 1 plus 1 y plus 1 dy rather. So we can let that equal to dz over 2, and then the denominator is just equal to z. Okay, then let's 3 integral of the numerator is just equal to dz all over 2, or we let the 1/2 outside the integral sign, and then y plus 1 squared plus 1 is just equal to z. Okay, so from here you can now easily see that dz over z is just equal to ln of z. So we have 3/2 ln of z, or equal to 3/2 ln of, what is our z? Y plus 1 squared plus 1. Then the other side we have the negative 4, and then we use the integral of leading to inverse trigonometric function, which is equal to arctangent of u, which is equal to y plus 1, and then all over the constant, which is 1, so all over 1, and then that's it. Then our plus c. Then overall we have ln 3/2 ln y plus 1 squared plus 1 minus 4 arctangent y plus 1, then plus c.